Welcome to this how to use a heat pump session and maximise energy efficiency and savings, part of the 2024 Open Eco Home season from Cambridge Carbon Footprint. I shall pass you over to Fiona from Green Heat Co-op to start you off.
Thanks, Siobhan. So good to see everyone here. Great to see what all the different heat pumps that people have in the chat. I guess just to say I have a 5 kilowatt Valent Aerotherm Plus, which I've had for a couple of years. There are some references to a few heat pumps in the slides that we'll see, but unfortunately there's just too many heat pumps to accommodate everyone. But most information, if you want something specific to your system, probably you can find that online. So just to run through the overview here, I'll give some slides on an overview of how heat pumps work generally and what is best practice for operating them. Then Nicola, who is an expert in building energy, Cambridge Carbon Footprint volunteer, and also a heat pump owner, she'll speak on the impact of heating schedule and level of insulation in your house. Henri is the founder of HavenWise, which is a company which has developed a smart heat pump controller, so he'll speak about that. And then lastly, we have Gary, who is a supporter of Green Heat Co-op and also a heat pump owner, and he'll tell us about his 1930s solid wall bungalow and how he operates the heat pump that he has installed there. So we have a lot to get through, and we already spoke a bit about questions into the chat. And thanks for saying hello and letting us know which systems you have. Just as we start, I'll say a bit about Green Heat Co-op. So that's a community energy social enterprise, which is based in Royston, where I am. So not too far away from Cambridge, but a little bit outside, a bit more rural. It's a non-profit cooperative company. If you are inspired to join as a member, we would obviously welcome that. You can support us in delivering events like this, as well as heat pump advice and home surveys, which is a service that we offer consumer outreach and education with this event and similar events throughout the year. And we also are currently undertaking or beginning the process of undertaking a community retrofit study of Royston and the surrounding villages. So we do have a household survey, which I would invite you to participate in. It's quite brief. You don't have to be in Royston or in the SG8 postcode to participate. There is an offer of a free home survey that comes with that, but that is unfortunately limited to people in Royston or SG8. But if you are a bit further out of Cambridge, South Cambridge, then you would be eligible for that. Without any further preamble, then we'll just start with an overview, a bit about heat pumps. This may be maybe less of interest to people who already have a heat pump and are well familiar with this. So we'll move along quickly, but do want to give that background if it's useful for people who are considering. So the first thing, why get a heat pump? Why think about this? The heat pump, well, changing away from gas heating or oil heating, if you have that, is the biggest way to reduce emissions in your home. You can save up to 100% of the carbon emitted by your home if you're so you've electrified your heating, and then if you can go on a zero carbon tariff, or if you have solar panels, you can basically reduce your emissions, the emissions of your house, to zero. So that's more carbon savings than a lot of other things that people might be considering for their home. Not that you shouldn't do those things, but if carbon savings are your biggest motivator, then a heat pump is the most impactful thing you can do. You can also make savings on running costs. We'll get into, that's really the meat of the presentation, up to £350 a year on the amount of energy that you're paying for. potentially more than that also if you can get off gas completely and don't need to pay the gas standing charge anymore. The other thing to mention is that the boiler upgrade scheme currently offers £7,500 off the upfront cost of a heat pump. So that is sort of an incentive to act in the next couple of years while that's available. I'll say a few things here on how is a heat pump different from a boiler. The key thing, and we'll sort of come back to this over and over, is that you're moving heat around rather than just generating heat from electricity, using it like a fuel. So you're collecting heat from your garden. I'm going to say a lot about garden and sort of thinking about an air source heat pump, but the principles would apply as well for a ground source heat pump or water source, if that is something that's an option to you. So you're moving heat, using electricity to pump the heat from outside to inside. And that means you can get efficiencies over 100% because you have a small amount of electricity that goes in and then a large amount of heat that comes out because it's collected the heat from the garden. Let's see. The other thing, or the next most important thing that we'll come back to again and again is that heat pumps are happiest when they're running slow and steady, when your house is kept at a nice even temperature. And this can be quite a change to how people are used to running their houses, with maybe a burst of heat in the morning and another burst of heat in the evening and shut off potentially when you're out of the house or overnight. So we'll be drilling more and more into why this is and how it works and what's the best way to set up your system to let it run slow and steady and get to very, very high efficiencies. Related to this, again, is the low flow temperature. So heat pump, it's sort of pumping heat up a temperature hill, and the lower that hill is, the cooler the waters can be inside your radiators, the more efficient it can be and the more heat can get from outside. But that means the whole heating system needs to work together. So it's not just a boiler that can get really hot and the other bits of the heating system, the radiators, the pipes, and so on, just sort of come along for the ride. Really, the whole system needs to work together. Hot water storage tank. If you have a combi boiler and don't have a tank in your house, then if you move to a heat pump, you would need to find space for one. A typical size of a heat pump in terms of the amount of heat they're delivering is between 5 and 10 kilowatts, although they're larger and smaller than this size. And you can compare that with a boiler, which would be 18 to 35, even higher kilowatts that boilers tend to be rated. Boilers are often sized for instantaneous hot water demand or to charge up your hot water tank very quickly, whereas a heat pump is sized to the demand of your heat loss, and therefore will take a bit longer to heat the tank, and that's also what makes it necessary to have the tank. It's just that the heat pump doesn't have the level of power available to give you a shower on demand. So when we talk about, if you're thinking about getting a heat pump, or if you already have one, it can be helpful to have a look at the way your system has been designed. Really, what you want is to have the system as simple as possible. So there are cases where you would need, you might need an extra tank, which is called a buffer tank, to accommodate a large house, or if you have microbore pipes. In that case, you might have additional pumps, but really an objective in system design, in heat pump system design, should be to make the system as simple as possible. Anytime that it's becoming more complicated, it should be for a reason, such as we're trying to deal with microbore pipes. This is a large home and we need to run multiple zones. Basically, the more complicated the system is, the trickier it can be to optimize. If it's a nice, simple system, then a lot of the guidance in here you can sort of apply straight away. If you do look at your system and do have extra tanks and pumps and so on, then things might be a bit more tricky and you may need to contact your installer to really get things optimized. So I have some example pictures here. If I can pull them up. This is an example from an installer that we work with. So this is the hot water tank. This whole thing will be covered up by a cupboard that is not put in yet. And they have some expansion vessels, and here and it connects to the connects into the underfloor heating in this case. And then here's an example of a more complex system. One thing to say is that a lot of these really small lines are actually electric cables, not pipes. So it's not quite as many pipes as it seemed at first glance, but we have the big hot water tank. We've got a smaller hot water tank over on the right. There's lots of valves, there's lots of pumps, there's just a lot going on. So if you have a heat pump and you think of, what does your system around your hot water tank look like? Is it, simple and not very many different components, or is it more on the, the more complex side? That's just helpful to know what sort of region you're in. The last thing to say about system design, so before we move into the details of operation for the heat pump, is again on the low flow temperature. So I just have a brief table here showing how a heat pump would behave at different design flow temperatures. So we talk about the design condition, which around Cambridge is about -3 degrees outside. And it's not to say it's never colder than that, but it would be quite a rare day that it was colder than that for the whole 24 hours of the day. So this is the temperature that the heating engineer is thinking about when they're sizing your system. And when they're choosing radiators, they're thinking about what is the flow temperature, the radiator temperature that you're going to need at that condition. As we move towards the left, the lower we get down that scale, then more of the heat that comes into your house can be from outside, and relatively less of it is from electricity. Of course, the heat that comes from outside is free. The heat comes from electricity, you have to pay for. You can see here at the bottom there is quite a difference then in running costs. The more electricity that you're buying, the more costs you'll have annually. With costs as they are now, the gas boiler crossover point is, I think, between 50 and 55 degrees, but you'll make, the more savings, the more you can push to low flow temperatures. I just see a question in the chat, which maybe I'll just pause on a buffer and a low loss header. We just quickly go back, or perhaps without looking at the picture. Buffer or a low loss header are basically a way of providing a separation between the heat pump and between the pipes in your house. So it's an extra tank that would be in your house in addition to your hot water tank. And that would sit between the heat pump and the pipes and radiators in your house. And it basically lets the two sides, they don't have to agree as much with each other. They can sort of each do what they like and communicate between the buffer in the buffer tank. But it's an extra piece of equipment and an extra complication in the system. So moving on to sort of the meat of our presentation here, operating your heat pump for performance and cost savings. I'll start here with the two principles of heat pump operation, which we've already spoken about a bit. The first point is that radiators can deliver heat more quickly. They can put heat into a room more rapidly if they're hotter. The second thing is that heat pumps are most efficient when the radiators are cooler. They don't have to work as hard to make the water as hot and get the heat from outside up to the high temperature within the radiators. So for best performance, what you want to do is replace the heat as it leaves your home. That means running your heat pump for longer at a lower flow temperature, keeping a more steady indoor temperature, which allows all the radiators to be as cool as possible, and generally keeping the radiator valves more open, not turning off rooms that you aren't using. You might need to turn rooms down, but we would advise against turning them completely off. I have a quick example here that is hopefully helpful. So if you have a typical house, which might have a heat loss of, say, 8 kilowatts at -3 degrees C, but most of the year, for much of the year, we have a much milder temperature of, say, 10 degrees, where the heat loss would be about half of that. So say 4 kilowatts at 10 degrees. If you imagine the house running for 1 hour in mild weather, it's lost 4 kilowatt hours over that time. So the heat pump needs to put back in 4 kilowatt hours in order to keep the indoor temperature the same as it was. There's 2 different ways you could do that. Well, there's many ways, but if we think about 2 options, one where the heat pump runs at 4 kilowatts for the entire hour steady. The other option, the heat pump runs at 8 kilowatts, but only for 30 minutes. So both of these options give the same amount of energy delivered. You have 4 kilowatt hours going in each case, but in option 1, the radiators didn't have to be as hot because the heat was going in more slowly. When you only had 30 minutes, they needed to be hotter to push that same amount of heat in half the time. So I hope this helps illustrate just the idea that when you're pushing the heat in as slowly as possible, then you can keep those temperatures as low as possible, which is what keeps the heat pump happy. We'll talk a bit about the sort of specifics, the practical side of dealing with your heat pump controls. I've laid these out as 2 levels. I should note this is not a standard thing, but I thought it would be helpful for this discussion. You could also call these level 1 as installer controls, and level 2 more of a consumer or a user control. But there will be cases where you as a consumer might want to access the level 1 controls, either because perhaps it hasn't been set up the best way by the installer, or because you want to make a change in how you're running the system. So we'll talk more about these on the next slides. The key level 1 controls are the weather compensation curve and the hot water temperature for the tank. And then level 2 is where you would access your weekly heating schedule, the hot water schedule, sort of the sets of controls that you're used to in level 2. So what we want for heat pumps to run at a very high efficiency is to use what's called weather compensation. So this is a system automatically done within the heat pump controls as long as it's activated. And when operating in this mode, the heat pump measures the outside temperature, or potentially looks it up online, or potentially does something even cleverer, which Henri will speak about. And it basically decides how hot it needs to run based on how hot it is outside. So just an example curve shown here, the outside temperature, and then how hot the heat pump needs to run. So as I said, in Cambridge, our design temperature is around -3. This seems to be an example perhaps from Scandinavia, where they might be at -20, -15 for their design temperature. But whatever the temperature, you automatically, the heat pump automatically decides just how hot does it need to be to balance the heat that's being lost from the house. So when you have colder weather, more heat is needed, the radiators are hotter, and you'll have a lower efficiency. But really, this is relatively few weeks of the year. And then when you're in mild weather, which is most of the year, less heat is needed, and then you can get a higher efficiency then, and that will balance out across the entire year to give you a better annual performance. The other thing to say on this is a simple on-off thermostat or on-off controls is not recommended for a heat pump. There are sort of third-party systems that you can put on top of the heat pump controls to sort of override them and turn on and off in a more simple way, but we really would recommend that you use the manufacturer's controls or something that has been specifically designed for heat pumps to work in this way. So a few simple tips for troubleshooting if you're wanting to improve the performance of the heat pump. The first thing to figure out would be, is weather compensation indeed activated? There's some links here, but the first thing would be to check the settings. You might need to go back to your manual or potentially speak with your installer, or if you could connect with someone else potentially from this session who has the same heat pump, and they might have had more experience with the controls and know how to do what you want to do. An indication that weather compensation is not activated would be if your rooms tend to be very cold in the morning, or potentially if they're very cold all day, that maybe the heat pump can't sort of catch up, having had the system be cooled off overnight. If your rooms are too cold, then I would advise, I guess, move sort of progressively down this list. The first thing would be open all the radiator valves, consider using a setback temperature, which Nicola will talk more about in a few minutes, but not turning the system off or letting it get quite so cold overnight would allow the rooms to stay at a warmer temperature in the day. You can also check your radiator temperatures. Your system might need to bleed the air out of it, or potentially a flush, and that can get your radiators operating more effectively if they're not blocked by air or sludge. If you've done all of those, then you can consider raising the weather compensation curve, so just moving everything up so it's just a bit warmer. The radiators are hotter at any given outside temperature. Or conversely, you could consider larger radiators that would allow you to keep that curve nice and low. If your rooms are too hot, I mean, you probably might not even realize that you may potentially be able to move to a lower weather compensation point. If you do have a lot of radiator valves that are closed and you find that you're just overheating a bit and wanting to turn the system down, then you can perhaps obviously just lower the temperature, ask for 19 degrees instead of 21. Partly close some of the radiator valves, which you're likely already doing. But if you find yourselves doing these things, then it's likely you may be able to lower the weather compensation curve, which would boost your heat pump's performance. Once you've done that, then you may need to go back and open up the radiator valves to sort of rebalance the heat that's coming into the rooms. I mentioned briefly there about checking the temperature of the radiators to make sure that all of them are working. You can do this with your hand. This is the simplest way. Does it feel warm? Hopefully not hot. You can get a simple laser thermometer like this one. You can borrow a thermal camera from Cambridge Carbon Footprint, which is another program that they run. There's an example here of someone checking on their underfloor heating. So there's a lot of heat coming through part of the floor, but in this section there's not enough water flowing through there, and so that there's no heat coming through that section of the floor. If you are interested in monitoring your heat pump in great detail, then Open Energy Monitor offers a heat pump monitoring system. There's a little sort of stylized diagram of this here, and Gary will show what sort of data you get out of that. Also mention heatpumpmonitor.org is a site where people who have this monitoring kit are making the performance and the operation of their heat pumps freely available. So you can, if you're interested, you can see what sort of performance different people are getting, and it really is amazing to see how efficient some people are able to run their heat pumps. Just skimming through things as we are conscious of time. On hot water, the same principle applies. If you can store the water at a lower temperature, that will let the heat pump run more efficiently. We often think, oh, the tank has to be set at 60 degrees, but that's not the case. For showers, you probably want a bit below 40 C. For washing dishes, maybe a bit above, but you're not actually going to be using 60 degree C water. You will be getting severely burned and scalded. The other thing is to make use of the time and temperature, the time controls for hot water as well as for heating. It's more efficient to run a full charge. So if your system maybe is charging twice a day, you could see whether it would be enough to just charge it once a day. If your system has an eco mode for hot water, that can improve the efficiency as well. Conversely, if you are struggling with constantly running out of hot water, then a way to get more capacity out of the same volume size tank is to store it hotter. You'll have an efficiency penalty from that, but that might be something that you're willing to compromise on if you have, a large family or teenagers or whatever the reason that you're needing a lot of water. Weekly schedule and setback. I'll just skip over this, and because we have Nicola speaking about this in a few minutes, and come on to towards the end and talk a bit about choosing the right tariff. So as efficient as you can operate your heat pump, it also helps. It can help quite a significant amount on costs if you have a smart tariff that's been designed to work with heat pumps or electric vehicles or even solar battery. But if you are using one of these sort of modern, innovative tariffs, there's a lot of savings to be made there. There's different degrees of these tariffs in terms of how much the user needs to interact with them. So you would want to consider how engaged are you able to be on a daily basis, or are you able to just sort of set up your system in a way that's compatible with one of these and let it run that way. So OVO has a heat pump tariff and an EV tariff that are based on the type of use. So it doesn't matter what time of day you're running your heat pump, you're always able to access low cost energy. Most of the others here are time of use, where there are a few windows of low cost electricity in the day. So if you can move your heat pump demand into those times, then you can access significantly lower cost electricity. If you have a heat pump and an EV and potentially a PV and a battery, you're really at the cutting edge of these systems, then you'll need to consider how much you're using each one. If you're driving, say you drive a lot and your house is quite small, it might be more favorable to go to an EV specific tariff, even if you have a heat pump. A few more comments on the Octopus Cozy tariff, which is very popular. You can join that with any tariff. This little picture here shows the different times of day and when the tariff becomes cheaper, when it's more expensive. So there's 3 cheap periods where the electricity is less expensive, and you'd want to move your demand out of the peak period between 4 and 7 in the evening, where it's more expensive. In my experience and from people I've spoken to, you can save 10 to 20% on your total electricity savings, on your total electricity costs with that tariff. The OVO Heat Pump Plus, as I mentioned, the savings only apply to your heat pump electricity, but they are fairly significant. So that could be an option as well, particularly if you're not interested in engaging with the time shifting. As of right now, you do have to have a valent aerotherm with that one, but potentially that may change in the future. Perhaps I'll just hand directly over to Nicola, who will speak on the impact of heating schedule and home insulation.
Thanks, Fiona. Most people tend to sort of heat morning and evening because they're out during the day and that sort of thing. In fact, they often heat the morning and evening even if they are in during the day. But some people heat all day, which I call once as opposed to twice, which is morning and evening. And this graph, which is based on modelled energy use, shows the kind of temperature patterns you're going to get with those heating patterns and a setback, and optionally with the setback temperature. So we talked about using a setback because it means you don't have this enormous leap in temperature when the heating comes on in the morning, and that a rapid rise in temperature like that takes a lot of power. The radiators need to be really hot. So to avoid that, we can make it more gradually by not letting the temperature the temperature in the house get so cold. Now there's two patterns here. We've got a green line, which is without the setback temperature, but this is with a sort of a terrace with filled cavity walls, you know, quite a nice cozy house, reasonably cozy house, and it's all got double glazing and it's got really loft insulation and it's not ridiculously drafty, but other than that it's sort of normal. And with this one, even if you set a temperature setback of 18, Fiona did mention having sort of 2 or 3 degrees difference in temperature between the daytime and the overnight temperature. So that's what we've got here. We've got 21, or well, it's 20 and a bit really, and 18 for the setback. And even when it's really cold outside, because this is on a cold day, especially during the day, it's got really cold here. The temperature in the house, in the terrace house, hardly drops below the setback. So you're not actually making any difference at all in the springtime and the autumn. And in the winter, you will use a bit of extra heat because you're keeping the house a little bit warmer than it would have been. But with the red line, we've got a semi-detached house with the solid walls here. Bear in mind, this is a cold day. It loses heat and drops in temperature when the heating goes off. And then we have this enormous climb in temperature. And if you do the setback, you have increased your heating demand considerably. Well, I say considerably, that's all a bit relative. If you are heating all day, so that's the sort of the once scheme, you can't possibly increase your demand by more than 10% over the year. I mean, you know, I haven't seen anything that would do that. If you are heating twice a day, then you've got this dip in temperature during the middle of the day as well. It can be a lot more. But having said that, that 20% is for a sort of a sprawling solid wall detached house with no wall insulation. So we are talking an appalling house from the point of view of heat pumps. So this is basically explaining that you will get an increase in heat demand, but you don't need to run your radiators so hot, which means you can run which means your heat pump can be more efficient. Now, getting this right is not a trivial exercise. Actually optimizing it, you hear of people operating it just on the weather compensation, and they basically have the controller is just on all the time, and what controls the heat flow is simply that when the temperature outside is warm, you know, as in mild weather you'll have a low temperature through the radiators, and in cold weather you'll have a high temperature through the radiators, and that controls the temperature in the house. But I wasn't quite trusting enough to do that, so I've still got a thermostat. But what you can do is get a smart heat pump controller. Homely was the first one that I knew of. Passive was the second one, and apparently we're going to hear about another one called HavenWise. Next slide, please. I've only got 3 slides, by the way. So my personal experience, we installed our heat pump about 3.5 years ago. It is actually only supplying space heating, so I haven't got the hot water complication. Initially, the room temperature was set to 20 during the day and 17 overnight, more or less. And that was fine, and it worked okay. And I had the nominal temperature for the flow temperature at 55. I can't remember what the lowest temperature was, but 55 is the hottest temperature for the radiators. And then I thought, well, I've heard about increasing the setback, and that makes things more efficient. So I tried increasing the setback, and lo and behold, the electricity and heat demand increased by about 10%. And I thought, oops, in order to get the efficiency, I have to turn down the flow temperature. So I reduced the nominal radiator temperature, the top end of the weather curve, down to 52. And the electricity demand was back to where we started, which means that there is no change in bill. So I haven't got extra savings, but we are warmer. And my beloved likes that, especially as at the time he wasn't very well. And, you know, he really likes being able to go to the loo in the night without freezing his socks off. So lots of people say that they don't like being hot in the bedroom. But I think what they mean is they don't like hot summer nights. Nobody likes hot summer nights. But 19 degrees is not excessively hot. I think you'd be surprised. Next slide, please. So, burning question, how much will my bills increase? Actually, we've had Fiona saying that they're going to reduce, but that tends to be more with the smart tariffs. But so for my calculations, given a sort of a totally average gas bill, I say a typical gas bill from off Gem, and a boiler efficiency of 0.9, so this is where you're starting from. That's actually quite conservative. That's quite a high performance boiler. And the normal approach is to assume 0.85, because even if they're efficient to start with, you're probably not running them at the temperature that allows them to be efficient. An allowance for hot water. And the heat pump SCOP is 3.1 for space heating, which is conservative. You can do a lot better than that. And 2.5 for hot water, which I think is ridiculously low, but we'll have to see. And gas and electricity price as per current price caps, which is a factor of 4 almost 4 between the gas and electricity. I reckoned this is your original cost with the boiler. This is what it would be with the heat pump, depending on your uplift in space heating. So if you've got a solid wall detached house, you're up at this end, and if you've got a nice cozy terrace, you're down at this end. You will probably see an increase in heating demand, but not so much for the nice cozy terrace. If, however, you come off gas completely and lose your standing charge, you can have an uplift of nearly 14% and still break even. And that's a pretty poor house. So, I mean, you'd have to have a lot of solid walls for that. Of course, you can do much better with specialist tariffs. They often expect you to have a little bit of flexibility on the temperature, so it can sort of heat you up a little bit extra when things are cheap, and you lose heat a little bit when they're expensive. But that works very well, and I know lots of people who use that, though I don't know anybody with HavenWise. And you can do even better if you've got solar voltaic, and even with a battery. Yeah, if you've got a battery that will cover the peak times, then you can go on those cozy things and do very well. So this is really, you know, total worst case tariff. Efficient boiler, which means that you're already, you know, you're delivering a lot of heat. If it was a less efficient boiler, then it's less heat to start with, and you can still break even, and if you've got a reasonably cozy house, or if you can come off gas.
Thanks very much, Nicola. I'll hand it straight over to Henri then to tell us about HavenWise.
Thank you, Fiona, and thank you, Nicola, for walking through your experiences and the complexities around that. So I'll tell you a little bit more about advanced controls. Fiona and Nicola both alluded to it already. But essentially, if we go to the next slide, Fiona, what it comes down to, your running costs for your heat pump are determined by 2 factors. The first one is your efficiency, which varies all the way from 150% to 500%, or the COP, the SCOP, as they call it. The second one is what you pay for your electricity per kilowatt hour, which can also vary, from negative prices really to very high prices, depending on what tariff you're on. So the question is, how can you be as high as possible on efficiency and as low as possible on electricity cost? And we've heard about weather compensation, and we've heard about setbacks, and we've heard about schedules and how much insulation you have, and what you need to do to tweak all of that. It's all pretty complex. And so if you go to the next slide, what it comes down to, or what you need to take into account is building characteristics. So your insulation levels. You need to take into account your schedule. How do you use, or when do you need heat and hot water? Your preferred temperature. Do you want 20 degrees, 19 degrees, 21 degrees? Weather. We've talked about weather compensation. Heat pump brand. Every controller is different for every brand. There's dependency on the tariff. There's dependency on solar PV and on batteries. So how can we make sure that people, for their specific home and their specific use case and all these specific parameters, how can we make sure that people pay the least on their heat pump bills? And that really is what advanced control is about. It's taking all these parameters into account in an automatic way, super easy for the user. It is predictive, so it looks into the future, looks at what is the weather going to do, what is your tariff going to do, what is your schedule requiring in terms of comfort, and optimizes all around that, and does that essentially all automatically for you. So that is what advanced control is about. And Fiona already said it. The traditional thermostats like Honeywell or Hive or Google Nest, they are not built for heat pumps. While they have smart features, they are not built for heat pumps. So what they do is they turn your heat pump on or off. And that is not what your heat pump needs. That is not what your bills need. What a good heat pump controller does is they modulate the heat pump. So they control the flow temperature continuously and optimally. So that is what we have built at HavenWise, and what Nicola alluded to, what others like Homely and Passive have built as well, although with a slightly different angle. If we go a bit forward, Fiona, you can skip over that. Yes, what that means. So what we have seen to date for our users is a reduction of 50% of their bills for their heat pump. And that is compared to when they are on a standard tariff without any optimal control. When they switch from that situation to a situation where they are on a variable tariff, and where they are using optimal control, the bill goes down by 50%, which is very meaningful for people, because that's multiple £100 a year, and means that your heat pump is going to be much cheaper than your gas boiler. So that really is what optimal control unlocks. I brought an example of what it looks like for one of our customers. I think that's the next slide. Yes, so this one. So this is an example from last Monday. What you see here in the top is the electricity price or the electricity tariff that customer has chosen, which is Octopus Agile. Octopus Agile varies every half hour. So every half hour, there's a different electricity price for that customer. And so you can see on that particular day, last Monday, it went from almost zero overnight to around, somewhere between 15 to 20 through most of the day, with then the peak in the evening. So what the heat pump, the way our algorithms decided then to run the heat pump is we made optimal use. If you go to the next slide, Fiona, we made optimal use really of that low price. So everything what you see on the left-hand side of that first vertical line, so where it says number 1, that's where the heat pump ran a little bit harder, and it ran because electricity prices are cheap. Then throughout most of the day, which is number 2, where electricity prices, let's say, were medium, the heat pump still ran. So it was still putting a little bit of heat in the building. Fiona called it low and steady or slow and steady. That's what that middle part is, number 2. A flow temperature of like 28 degrees, super efficient. Number 3 is then when that price peak happened. And so because of the fact that we know how much heat we need to put into the home, we are able to avoid that price peak. And so what you can see, we barely, a little bit at the end, but that's really pennies. We barely heated during that price peak. And number 4 that you see there, that's actually a hot water cycle. So also we moved the hot water heating into that cheap price period. So what that meant for the customer is for that particular day, last Monday, the customer paid £1 for heating and hot water. His home was comfortable at somewhere between 20 and 21 degrees. And if he would have been on a standard tariff without any optimal control, he would have paid £4. So that's for that particular day, it was a 75% reduction. But in general, it is a 50% reduction. So that is an example. So it's really about the algorithms that we've built. They look into the future. They know what your house needs in terms of heat, how it reacts to the heat pump, how it cools down. It knows your schedules. It knows your electricity tariffs. And it just makes sure that you're comfortable at the lowest possible bills. If we go to the next slide, what we have tried to do is to take all the complexity for people away with respect to weather compensation and schedules to be set up in the controller of the heat pump and hysteresis settings and setbacks and where to set your setbacks. All of that we've tried to take away. And so the way it works is that for homeowners, we just have a very simple phone app where they say, between that and that time, I want that temperature. I want hot water in the morning by 7 a.m. and again by 6 p.m. And that's it. That's what we take as an input for the homeowner. So you don't need to worry about any of the the more technical terms that an installer would typically set for you. So that's about the simplicity. And then if we could just go to the next slide. I'll just be very quick. The benefits of advanced control is reduced energy bills. It is easier control, through the app instead of the complex controllers from the heat pumps. The way we approach it is we are software only, meaning there's no extra installation, there's no extra hardware, no extra kit to buy. We also have built-in anti-cycling measures, meaning your heat pump will actually extend its lifetime beyond what normally would have been. And yeah, we are very approachable, and we're very fast in answering questions as well. So that's the benefit for the homeowners that we see. And then very last, because I'm conscious of time, next slide. Yes, so we are compatible at the moment with 4 brands: Vaillant, Mitsubishi, Samsung, Daikin. The requirement for us is that your heat pump is internet connected. We are working on adding other brands, but those are the 4 that we're currently supporting. Hope that was a bit clear, and hope that gives a good overview. Fiona, over to you again.
Great. Thank you, Henri. Really interesting stuff. And lastly, Gary is going to tell us about his home and his heat pump journey.
Yeah, thank you. I'll probably whiz through a lot of this because I think other people have mentioned this. So we bought this in 2021. It was a fixer-upper. It had been pretty well neglected, so it needed loads of upgrades. And so first year we found it was impossibly cold. It's a solid wall house, really drafty. Windows had blown, were really old, etc. So clearly there was a sort of a plan needed, and we took a sort of a approach after being so miserable in the first winter about how cold it was to do something really quite positive about it. You'll probably notice from that the roof, we could see the light through the roof from inside the loft. when we did the loft insulation. So that was a job for the following spring. So we did the loft, but at the same time we have a loft conversion. So we upgraded that to a warm deck and made sure that that was, if you like, one of the first things that we completed. So if we go on to the next slide. Because it was so cold in that front room, particularly, it's got 3 outside walls. We decided to try underfloor insulation in that room. And yeah, you read about internal, external insulation, whatever. We thought the floor was something we can do. And so we embarked on this. We used the ecological building systems method. You basically make a series of hammocks between the joists, fill it full of insulation, and then tape it all around the edges. So it's absolutely draft proofed. So we did that ourselves, a matter of pulling up floorboards and putting that down. The pictures on the left are that front room with the 3 outside walls. We were so happy with that. We did the back room and the hall and the little room and pretty much everywhere we could get access to. So, so we pretty much insulated under the entire floor, other than a very small bathroom that's downstairs, and it's made a real difference to the draft proofing. So perhaps if we move on to the next slide. So we sort of took an incremental sort of approach to this. So we live in a conservation area, so you'll see from the solar panels there, they had to be flat, so they couldn't be seen from the road to comply with the conservation area. And that is on a garage that is only big enough for a toy car, really. It's a 1930s garage, so you couldn't actually see those panels from the road. So so we have 4 panels on the garage, 6 panels on the flat roof. That's the full extent of the solar that we put in, but we also took the opportunity to have a 10 kilowatt battery. So I know that's been mentioned a couple of times, but perhaps as we get forward, if you keep that in mind, because it does make a difference, I think. So if we go on to the next slide then. So here's our heat pump. So we, because we did the solar and battery, and we had that through the winter, we were so happy with how that reduced our energy bills. We moved to an EV in that October as well. The combination of the Octopus Intelligent Go tariff overnight, so between 11:30 and 5:30 a.m, the electricity is at 7p a kilowatt, and then you pay outside of that. But our 10 kilowatt battery basically worked through the day, and we didn't use any premium power kilowatts outside of that 10 kilowatts. And if you like, the efficiency savings in moving to an electric car from a Polo was staggering. So like a couple of £100 a month in petrol were now pence, really, in comparison using electricity. So that was a real bonus for us. And we thought, well, actually then to make the full transition, the air source heat pump is the final piece, really. So we did a lot of work. Fiona was really helpful in that and put me in contact with a guy, LibTech, you can see a small sign on the bottom of this, who did a heat loss survey. Because of our fixer-upper status, all of our radiators needed upgrading. So we had to take that on the chin, but it was a good opportunity to upgrade to some quite fancy column radiators in fitting with a house, rather than the rusty things that had been there before. So we didn't change any pipe work. That's the original pipe work in there. The radiators were simply joined on to the pipe work was there for the existing radiators. We chose this heat pump because there was a few examples of how it had worked quite efficiently with old buildings. So that was quite good, given we've got solid walls and a conservation area. Exterior insulation is going to be pretty difficult. Interior insulation is pretty difficult, and so we thought we'll give ourselves the best shot with this particular heat pump. So this is a 6 kilowatt heat pump. We've had it since the middle of March. It's worked phenomenally well. One of the things I think certainly a change for us is the level of comfort. We used to turn our heating on, and then we have that cooling, like Nicola said, we'd have a rapid cooling, then we'd turn it back on again in the evening, and we got these really intense burns trying to heat the house up. We now have a very stable, very even temperature, 24 hours a day. And because of that, our flow temperature is incredibly low. And so The radiators, when we had a gas boiler, were burning hot. You touch them and it'd burn your hands. Now they barely feel as warm as your hand, and that's quite. It's almost eerily weird, but our house is constantly warm. So it's quiet. I have to check that the fan's on by putting my hand next to it. It's cheap, and I've got a few slides beyond this that sort of maybe show that. It's in our side driveway, and as I said, our side driveway isn't big enough for a normal car. Maybe a 1930s Morris Minor or something like that might have got up the side of our house, but nothing new. It can't even get through the gate. So this is about as big as our wheelie bins that we store in that side access. The pipework goes straight up into the loft. Fiona showed some examples of hot water tanks and the pipework there. Ours is quite straightforward. It's got a white box similar to a boiler in the loft, and then we have a water tank next to that with a few pipes. There's one buffer vessel, but that's tucked behind in the loft. So we don't have any of that downstairs. It's all up in the loft. The install, as I said, had all radiators changed. They're much bigger, but they give out a lower heat. Our water tank is 140 litres. We heat that once a day, and I'll be able to show you that on our on the graphs that are going to come up. We have a water.
Sorry, Gary, I'm just a bit conscious of time to not keep people too late. Is it all right if I?
Move on to the next one.
Hurry you along. Thanks.
So this is Fiona mentioned Open Energy Monitor earlier. This is a screenshot from that. We set our daytime to 19, our nighttime to 18, so only 1 degree between. It's on full weather compensation. We don't touch it other than when those higher temperature comes on, 1 degree. It's hardly noticeable, to be honest with you. And you can see that spike at 1 a.m. is when our hot water gets heated. And the other red bits are when the heat pump actually comes on. So the purple line is the outside temperature. So you can see it's got cold, heat pump comes on, it got warm, bit warmer, it goes off, and it just continues like that. As I said, we're on Octopus Intelligent Go. I've just checked our home battery today because the sun's been shining a bit. It's on 78%. So we charged up during the night. We've used some of the battery during the day. The solar's topped that up. And even with cooking an evening meal and the air source heat pump being on, it's at 78% now. So we've yet to try it through the winter. I'm sure we'll have some moments when we're into premium electricity, but it's whether the cost benefits of buying additional batteries or remaining on that tariff or changing tariff will work out. And we need to do that equation, really. Move on to the next slide. So this is the whole lot. This is the entire lifespan. There's a gap in July when our Wi-Fi broke up with the Open Energy Monitor and we had to get it hardwired in. But as you can see when it was heating and the SCOP was sort of up fairly high. Then when it's doing hot water only, it's quite variable. And I don't understand why it's so variable, because it's maybe heating different water amounts at night. And then we've just come back into heating season in September, and that's very much depends on the temperature, the purple line, how much energy it uses. Then I think, is there another slide, Fiona?
I think this is.
Oh, right. So this is the costs. So I did some stuff on how much our gas was in 23 and how much our electricity was in 23 until we went with the battery, and that was October. Solar and battery got fitted. I should have done the difference in solar and battery then, but you can see that from sort of an average bill of 60 and 70 pounds a month, it dropped to 48 in October, and that's when we had the battery fitted and moved to that EV tariff. But you can see that our gas was still going up there, where you can see the corresponding electricity 24 costs are, bearing in mind our heat pump came in this March, 55, 57, and then a slight increase in April. And then during the summer, when solar has been there, our solar export has paid for majority of our bill every month. And this, I think this last month, the total bill was not very much at all. So You can see the benefit of the solar and the battery in using a heat pump, especially when the sun's shining. But I'll let you know how things get on in February after some dull, hardly light months go on. But I know you're pressed for time. But this is our experience, and that is the real thing. And if you like, Octopus Energy came along and got rid of the gas meter for free, about a week after we had the heat pump fitted, and that's what you get left with. I put the white box back, but there's nothing in it. So if there's any questions, happy to answer them.
And the next one is from Libby, and it was more an expression of frustration trying to find a company to service their LG heat pump. Has anybody got some suggestions or support for Libby, who's found it very hard to find somebody to service their LG heat pump?
Have you looked for a Heat Geek registered plumber? If you go on the Heat Geek website, there's a series of air source heat pump trained people. They might be it gives it a map of the UK, and you can zone in where people might actually work.
Thank you, that's great. I haven't. I use a company that just don't know much about LG, and all the handbooks are so difficult to understand because they're translated from Korean or something. So it's really hard to follow. But I'll look at Heat Geek. So I can find that Googling it, can I?
Yes, Google Heat Geek, absolutely. I'm going to move on to Hermione now, who has recently bought a new home, won't be moving in until December, and is wondering about how to manage using a heat pump, I believe. Hermione, do you want to ask your question?
It's not actually me, it's some friends of mine who were asking me, because I'm looking into heat pumps, how to do it. And I said, well, actually, I don't know that one, because it seemed that if you just had it on absence, it was just wasting heat because you're not actually there. And maybe it's back to this empty rooms, but this just happens to be an empty house. And I just wondered if anybody had any experience, because I couldn't see, looking at their manual, how whether it was okay to leave the heating off completely, given that there was some glycol there that's supposed to be going down to -10. Will it look after itself without having the heating turned on, or is that not a sensible way of dealing with an empty house at this stage?
I mean, if it has glycol, I guess there's a few things. If it has glycol, it is, it's unlikely. Number one, it's unlikely to get as cold in the first place, right? We're unlikely to have that low temperatures for that long. Secondly, if it does have glycol, then it should be able to sort of, it would be protected. There is a absent setting where you can turn down the temperature to, say, set it at 10 degrees or some temperature that would be where the house might settle anyways most of the time. Depends maybe if it's detached or if it has some residual heat from, if it's a semi or terrace. Another choice would be to leave it off maybe, and come back in the middle of November or something and put in a bit of heat.
Yeah, it just seemed to be that with the instructions that have been given, because it was only installed in 2021, that it shouldn't be set lower than sort of 17, 15, because the system had been set up to normally run at 15, and if it was any lower than that, it was going to get itself in a twist. And
no, I wouldn't expect that. I mean, really, right? No one's there. It's just to make sure that the system is safe from frost. It's the only concern. And then when they come in, then they can worry about 17, 20, and so on. Yeah,
that's really helpful. Thank you very much indeed.
Brilliant. Thanks, Hermione.
On the unused rooms thing, I don't have personal experience, but I have looked at the issue. Unless someone else wants to take on, I'll just say a few words.
Yeah, go for it.
So the problem with the unused rooms case is because you've got internal walls between the unused room and another room which you are heating, and heat leaks across. And if you don't take that into account, so that effectively means that in order to maintain the temperature that you want in your, I don't know, bedroom 1, say, while bedroom 2 is not heated, then because of the extra heat leakage, you're going to have run the radiators hotter in bedroom 1. But if you have a smart enough controller system, you will end up with running the radiators hotter than you would otherwise have done. But if you don't have a smart heating controller, you'll just be a bit colder in bedroom 1 because it's leaking heat into the unused room. So it kind of depends on your setup a lot, but you may be losing a little bit of efficiency because there will be heat leakage through. And by the way, I'll put a link to a blog post of mine on the subject. Or you may find that you're just a bit cold in that bedroom 1 because of the heat leakage.
Great. Thanks very much, Nicola. Brilliant. Now we have a question from Yuha, and they're planning to get a heat pump in the next few months. They want to know if there's any new tech coming on board. Should they wait, something that's more efficient or quieter? What's coming up in terms of new tech for heat pumps?
That's a good question. There has been, so it sort of depends on, each brand has its own sort of cycle of updating the systems, and some of the brands that tend to be most popular have just had an update. So Valence, for example, Samsung's have just had a refresh, which tends to mean they have a very the sort of most modern refrigerant that someone was mentioning right in the chat, the R290, which has very low global warming potential. The ones that have been recently refreshed also tend to just look nicer and are quieter because they've put the effort in to bring the sound down. So I think right now there are a good range of systems that have just been refreshed. If you did have your heart set on a particular one that was looking a bit dated, then there's a potential to wait. I do think a lot of the innovation now is things like HavenWise is sort of, it's in the tariffs, it's in the controls, the things like making it quieter are at this point, I'd say, sort of tweaking around the edges, and the big innovative changes are more on the controls and the sort of how do you run it, how do you save on costs on that side.
Brilliant, thank you. ENC's also gone ahead and asked, post Henri's presentation, temperature nodes, how many temperature nodes are recommended for HavenWise, and what analysis to HavenWise undertake to determine the number of temperature nodes? Henri, do you want to answer that specifically? I know you replied to Ian, but this is a post question that might be interesting.
Yeah, so we currently do 1 temperature node because we see that is the optimum for most homes. If you do have a large home, then you might need multiple zones. But in general, 1 zone is typically the best solution for people, except if you have a big house.
And yes, and that's everything. So thank you very much.
Thank you so much. Thank you, Siobhan.
Thank you.
Thank you, everyone.